Okay, Mr. Long, FAQ number 3. Okay, draw and label a free body diagram. Might work. You have f of g, you have f of n, and we have the force F here, so when we draw it out, you have Fg, which is equal to Fn because it's not going up or down, or it's not equal to Fn because we have this F force too, which is going to go in this direction. And this component plus this component is going to be that component, so let's draw it relatively bigger here. So then just cut it off, so it'll be like about here. It'll be about here. So this is gonna be F. It's gonna be Fn, and there's gonna be Fg. So 3 forces on it. 1, 2, and 3. And then we have friction force because there is a mu k. So it's gonna be going this way, or like this. Those are the forces, 4 forces. Fk, Fn, Fg, and the force F, the applied force. Yeah. Should probably make this force bigger, so it's a little bit more on this way, so that it has more force than the friction force, because the friction force is going to be less than the applied force in this direction because it's going to move this way, right? It's probably going to move this way. Okay. Those are going to be all the forces, the 4 forces, and F is going to, of course, have components. But since we don't draw that, then this is it. And then for part B, we're going to have any more quantities. Since the acceleration is in the x direction, since it's not accelerating up or down because it's on the surface, it's not going to be on the vertical axis, so we're going to use the horizontal axis, which is going to be the 2x, because of delta x is equal to vi t plus a over 2t squared, but in this case vi is 0, so this is gonna not be there, so we'll just simplify it down to delta x, or x of t in this case, is equal to a over 2t squared. And since we want a by itself, and we're gonna be able to plot that later, I'm gonna isolate for a, so it's gonna be multiply both sides by 2, so 2x equals at squared. You divide t squared, so that a is equal to 2x over t squared. And t is going to be on the x-axis, of course, and x is going to be on the y-axis for those data points later. But right now, since we only need it's asking what we're going to use. We're going to use 2x and t squared for the horizontal axis. So remaining rows to label each one. And yeah, so there's gonna be 2x, there's gonna be t squared. And I plugged it into the calculator already beforehand. And these are the values that we're gonna get right here. So 0.072, and it's of course in meters. And it's gonna be in seconds squared because of the squared here, right? So quickly gonna fill this out. And the time is gonna be ease. So that's gonna be all the values that we need, and we're gonna plot those values down. Because of course we're trying to graph the acceleration. So we're gonna use the our y is gonna be x of t, and which is gonna be in 2x, and that's gonna be in meters, right? And our x direction is gonna be time, which is t, which is also gonna be in seconds squared. So s squared, of course, from here. And we're gonna have the time intervals be these, or those are gonna be where the data points we're gonna plot, the x and the y. So this is gonna be the x, and this is gonna be the, no, wrong way. This is gonna be the x, and this is gonna be the y for this graph. For on the y-axis, it's gonna be the x-axis. And just gonna take the biggest value, round that up to 2, I guess, and divide it by the 5 boxes to use the graph completely. We're gonna have 2, and 0, from 0 to 2, 0.4, 0.8, 1.2, and 1.6. And yeah, so since 3 right here, we'll just run it down to 3. We'll go above a bit later. You can always do that. And the rest of the values, we can just go from 0 to 3 divided by 5. It'll be about 0.6 each. Make that look nicer. Now we just graph the data down. It'll be 0.4 and 0.072. It'll be about somewhere down here. And then we have the second point. Be somewhere right here, about right here. And the third point, which is gonna be somewhere right over here. Next point at 0.8, about 0.81, be about right up here. And we have the last point, 1.69. It'll be somewhere over here. At 3, a little bit above. So there is a good place. And we take a best fit line, because draw the straight line that best represents the data. Be straight like this. Try to draw that straight. That's the straightest line I can draw. So then, yeah, first side completed. And we'll move on to the back side. So for D, find A of X through calculate the experimental value. Let's go back to the front side here. So to find the experimental value, we'll probably take the average between all these points, right? So we just take, because this is a line, just take the point from here and here. Point right here is going to be 3.042. And then it's going to be on the time of 1.69. Then it'll be subtract the other beginning time, which are these points, which is that point. And this should approximately be 1.8, or exactly 1.8 meters per second squared in the positive direction, which is this. Take the line of motion as the positive direction. So this way is the positive direction. And then, yeah, that's gonna be the acceleration. And then the next question, using Newton's second law, derive coefficient of friction in these terms. Okay, so let's set up the equations. We're gonna have net force of F is equal to ma of x, of course. And for the y, we're gonna have net force y is equal to 0, because it's not moving up and down. And this is gonna be around, or this we can expand to Fn in the positive direction, which is up, minus the F, and this is also theta right here, so we can do cosine, right? Or sine, of course, for the y direction. Sine of theta. And then we have minus the FMG, or the F of G. And all that's going to be equal to 0. And since we are deriving the mu, we need to look at the x direction, which is going to be the F force and the Fk. So we're going to have Fn cosine for this. And that's going the positive direction, so that's going to go first. We have F minus Fk equals ma of x. And we're going to mu k, so we're going to expand this Fk. Or we don't even have to, we isolate Fk, right? So Fk is equal to Fn cosine of theta minus ma of x, and we have isolate Fn, and that's equal to f sine of theta plus fg, which is going to be mg, right? And since we know that mu is equal to, or the coefficient of mu is equal to Fk over Fn, you just replace Fk and Fn onto those, and we have mu is equal to sorry, I don't know why I put Fn here. Should just be F here. Got a little confused, you know? Just noticed it. It was a big mistake. Could have messed it up. Glad I caught it. We're gonna have Fk as this, so F cosine theta minus ma of x all over F sine of theta plus mg. And that should be the equation. And then it's in those terms already, so that's good. If they apply that, find the kinetic friction. Well, we already have kinetic friction, right? We already have the equation for that, which is just this thing. So F cosine minus max. And since let's just write out F cosine theta minus max. F cosine theta ma of x equals fk. So we have f is 12, just plug that in. Cosine of theta, which is 60, minus max. Well, mass is going to be 2. A is going to be 1.8 if we use the experimental value. That's going to be equal to fk. And fk is going to be 2.4 newtons. And since it's opposing the line of motion, because, you know, it's going this way, it's going to be negative. There we go. That's fk done. Find the coefficient kinetic friction of mu k, or of the coefficient of kinetic friction. Well, we already have the equations from part E, right? So we can just plug it straight in. And we know that F is equal to 12. Theta is equal to 60. And then we know that A is equal to 1.8 if we use our experimental value over here. And we also know that mass is equal to 2 kg. Okay. So now we can just plug all that into this, and this should be pretty easy. G is gonna be 9.8 because that's the acceleration due to gravity. And so mu k is gonna be approximately it's a plus sign. Change that in a bit. And the mu is gonna be 0.08. And that's how you find the G, as you solve G. And moving on to H, if the applied angle is decreased. So this is decreased. Well, if that's decreased, then the angle that we're pushing on an object, right, is gonna, if that's decreasing, then, since it's Fg plus the force of theta, and, how do I put this? If you push on an object down like this, the more you push directly down, it'll be there's gonna be more mu, right? Because your Fn is gonna be higher because it's your mg plus that extra force. But if you push on it more sideways, then there's gonna be less force pushing down. And that makes sense because if you do take this as sine, right? Sine of theta. If you do sine of 60, which is what our regular is, be 86. But if we do sine of 30, it'd be 0.5. So it'll be less, right? So there's gonna be less force down, plus the mg that doesn't change. So Fn is gonna be less than the previous, right? And yeah, if there's less Fn, there's gonna be, the friction is gonna be smaller because Fk is reliant on Fn, and the mu is gonna stay the same, right? No matter how you look at it, it's gonna stay the same. Coefficient mu is gonna stay the same. So if Fn is decreased, then Fk is gonna be decreased. And if there's less force pushing this way, it will accelerate this way faster. And since this force, it's gonna be pushing, instead of it arrow being like this, it'll be slanted like this, right? It'll more curved. So this will be bigger. Try as a dashed line. This will be bigger, right? The component in the x direction will be bigger than this component, right? So it's gonna be that extra force that's the force in x direction, plus less friction, so there's less force opposing that. That means that acceleration is gonna increase. So acceleration is definitely gonna increase there. And sketch the acceleration versus time graph. Well, it's t and it's a of t. Acceleration is going to stay the same, right? So it would just be a straight line across. Let's use a brighter color so you can see this better. Be a straight line across, and it'll be the 1.8 meters per second that we had, which was the experimental value, of course. Yeah. Okay. Draw the velocity. Well, since that's acceleration, that means that the velocity has to be a linear line, right? Be straight up like this. Because the area under the curve is slowly increasing as time goes on. So slope will be increasing. That's true because if you take the integral, this will be a squared, or this will be a regular x function, right? It'll be a linear function. And the position versus time graph, well, since we have the points already, right? We have these points. You can just graph that to find the actual function. So we don't need this calculator anymore. Graph the points. It's gonna be, and since it's gonna be like this, we just use the 1.3, I guess, since it's fairly easy to use. It'll be about 0.26 per interval. Okay. And for the x, it's gonna be 1.521. Just round that down to 1.5. So it'll be about 0.3 per. And then we just graph the points. It'll be 0.2. Try to get this super accurate. Be somewhere on this line. 36, so it'll be up here a bit. Get that. 0.51. Be somewhere over here. 2. Oh, that is not right. Should be super low down here, actually. Be down here somewhere. 0.51, so it'll be here. Up to about up here. 74. I'll be about down over here somewhere. And it's gonna be 0.49, so close to 0.5. be about here. Somewhere there. Should be on here somewhere. Okay, then we're gonna have 0.9. Here and then 0.7, so somewhere up here. Let's go about there, should be enough. For this one, 1.3, 1.5 will be here somewhere, right? So that does not seem right. Well, the graph would still be something like this, right? Because be a parabolic graph, something along these lines. It's gonna be the x of t. This is gonna be t in meters and seconds, and these are gonna be in t, which is seconds. And this is gonna be v of t, which is gonna be in meters per second. This meter per second squared versus t. And yeah, that's the FRQ number 3.